Hello, I'm Sho Takatori. Today I'll talk about a project led by members of my lab. Sachin Nagela and Daeyoung Kim are the two co-first authors of this project. Saksham Malik is a PhD student who is co-advised between Professor Eric Shakfe and myself. So, this really cool movie you see right here, let me explain that. We have two optical laser tweezers, which are used to confine colloidal scale micron particles at a particular point in space. So each laser can trap a single colloidal particle at these two fixed positions. And I'm going to take the outer trap and translate it at some prescribed velocity u1. And this setup is immersed inside of a Newtonian incompressible fluid of water. And the setup is placed inside this bulk solution, far away from any boundaries, far away from the interface. Now, if we translate the outer particle, it's going to entrain some fluid flow around it due to the no-slip boundary condition, and you're going to create a flow around the translating particle. The unique thing about optical laser tweezers is that it generates an external force that keeps the particle to a particular spatial position, but it does not generate external torques on the particle. Therefore, both particles are free to rotate inside the fluid. Center particle should feel the force coming through the fluid. It's called hydrodynamic interactions. And if it responds to that, maybe it will cause the center particle to spin with an angular velocity omega 2. That's what you saw in this movie on the title page. This is a movie of the postdoc in our lab, Daeyoung Kim, who worked hard to create this setup. And he half-coated and painted the particles so that we can see the orientation of the center particle as it rotates as a function of time. Now, everything I'm going to show you today is going to be at low Reynolds numbers. So the Stokes flow equations apply, and the equations are linear. What Daeyoung did next is to conduct this experiment over a variety of separation distances between the two traps. Here we have the smallest separation of the center of the bead to the translating bead. That center-to-center separation is 6 microns, and we can go all the way over here to a separation distance of 20 microns, and you can see that the center colloid is moving very slowly inside the far separation, but rotating very quickly when it's very close. So we can plot the angular velocity of the center colloid, normalized by the velocity of the translating particle, and plot that as a function of the separation distances. Now, the cyan color points you see here, those are direct experimental data coming from these movies. We literally go to these movies, measure the angular velocity, normalize it, and plot it. That's what we see here. Now, a very talented PhD student who recently graduated, who is now doing a postdoc in our lab, developed a nice theory to make predictions of this result. The idea is we have one particle with a prescribed velocity and one particle with 0 torque. So it's a mixed mobility resistance type hydrodynamic interaction calculation that can be worked out for two particles. And for the long-range far-field theory, that's what's shown here in white. Now, the near-field theory is a situation where the two surfaces of the object are close together. And in class, we do this classic problem of a surface approaching another surface, the Reynolds problem. But in this case, we're doing the translational shear problem. Now, it turns out that this problem scales as the log of the separation distance. That's what's plotted here in yellow. And as you can see, the experimental data agree very well with both of those theories. So this is a very nice and very precise quantitative experimental setup that allows us to directly measure hydrodynamic interactions between colloidal objects suspended inside of a fluid. And we're not limited to just two particles. We can have many particles. We can have 3 particles where you can clearly see that the particle on the right rotates quickly when the translating particle is next to it, and then slowly when it's far away. We can also have 7 particles like this. It's a very cool experimental platform that allows us to probe many body hydrodynamic interactions of colloids suspended in any fluid. Now, let's go to any fluid. So far, we've been talking about an incompressible Newtonian fluid of water, but we can do this for any fluid. Why not sprinkle in there a little bit of surfactant, which can self-assemble into a worm-like micelle. It's a very interesting type of polymer that is very fragile and floppy and flimsy. It can have nanometer diameters and hundreds of nanometers or microns in length. So it looks like a slithering worm. And at sufficiently high concentrations, they can form an entangled network. It's called worm-like micellar networks. It looks something like this. It's somewhat similar to a normal viscoelastic polymer that can form entanglements and reptation, except this polymer is made up of small little surfactant molecules, so it's very floppy and flimsy. They can break, undergo fission, they can undergo reptation and entanglements as well. So all those processes are happening together. And if you take this material, slap it into a macroscopic conventional rheometer and do linear rheology, so small little deformations, you can measure what is called G prime and G double prime, which is the storage and viscous modulus. So G prime is a measurement of how elastic this material is, and G double prime is a response of how viscous this response is. And so whenever you have a material like this that exhibits both elastic and liquid-like properties, it's going to have a plot that looks something like this. And what's also unique about this particular material is that despite having so many length and time scales, for linear rheology, there is a curve that looks just like a Maxwell fluid. So this kind of plot is a classic Maxwell-like result, where the crossover point between the two curves tells you the crossover from the elastic to the viscous response. And for this particular fluid, it's about 0.1 to 1 second. So it's about less than a second of the crossover time from solid-like response to a liquid-like response. So we can do this experiment where you have this viscoelastic worm-like micellar solution contained inside the solution. And what we're going to do is to do a relaxation experiment where we have this outer particle, this located by this green cross, is suddenly going to be translating around, and it's going to do several rotations and then suddenly stop at the end. We're going to keep track of the angle of the center particle, as you can see located here with the red circle, and plot that as a function of time. So here it is. We're going to step the outer particle. So here it goes. And down here, the angle wraps around from 0 to 2 pi. It's periodic, so it goes back down when it goes to the top. And then we stop the outer particle and look at its response. So it's a relaxation test. Let's play it one more time so you can see the whole behavior. We step, we do several rotations, and finally we stop. Okay, so there's lots of interesting things happening to the data, but I wanted to focus on 3 distinct sections. First, what's happening at early times in this small little sliver, and then what's happening at steady state, and finally what's happening at the very end where the translating particle is suddenly frozen. Let's first focus on this early time behavior. If I were to zoom into the small little sliver and zoom out so that we're now plotting the onset of the starting of the driving of the outer particle. On the y-axis, I'm plotting the angle subtracted off from the starting angle. For Newtonian incompressible fluids like water, as soon as you start moving the outer particle, the center particle immediately starts to rotate. So it's an immediate response at time t equals 0 offset and immediately starts to grow. And you can see that directly from the experimental images. For water, as soon as you start to move it, the outer particle is moving, and you can see the slice of pie that's being carved out. That's the growth of the angle from this time to this point right here. In contrast, for a viscoelastic worm-like micellar solution, there is a delay to the onset of rotation. So even though the outer particle is already moving, the center particle, it's as if it doesn't even know that it's moved yet, because there's a little bit of relax or transient buildup and memory associated with the velocity field, and therefore it doesn't respond as quickly. Now, if you look at the experimental images, you can see that for the same position of the outer colloid as the incompressible Newtonian fluid of water, you can see that the slice of pie that it's drawn out is smaller for the viscoelastic fluid. That's because there's this memory effect that it takes some time for the center particle to respond to the particle driven very far away. Now, Sachet developed a theory for the two-particle mobility resistance hybrid coupled problem in the case of a linear Maxwell fluid, and used that linear Maxwell fluid constitutive equation, did the exact same problem, and obtained this yellow solid curve. And it fits very nicely. And from that, we can extract a relaxation timescale, which we obtain for this particular solution to be about 310 milliseconds. Now, we can also vary the relaxation time, as I'll show you in a little bit. But at long times, we find it's the slope, which gives you the angular velocity of the center particle, is about the same between water and worm-like ice cells. In general, viscoelastic fluids could have and often do have a different steady velocity compared to water, but in this particular case, it just happens to be the same. Now, like I just said, we can perturb this relaxation and memory effect very easily, for example, by adding a little bit of salt. When you add salt into the solution, the worms are negatively charged, so the salts can cause the worms to collapse, increasing its elasticity. And when you increase your elasticity, this curve can actually even take an even longer time to respond to motion happening very far away. Now, what's really cool about this measurement is that we have a direct and precise measurement of time-dependent hydrodynamic interactions. Usually, for water, you could just take a picture of where all of your particles are located, and just by knowing the position at an instantaneous snapshot, you can calculate all the hydrodynamic interactions between all the particles. But for a viscoelastic solution, each colloidal particle has a little time convolution happening everywhere, so an instantaneous snapshot does not give you a full picture of the forces and stresses inside that material. And now we have an experimental direct quantitative method of precisely calculating those time-dependent interactions in a many-body sense. So it's a very cool quantitative method that gets at a time-dependent hydrodynamic function determination. Now, for early time, we saw that there was a little bit of memory effect. At steady state, we saw that the two curves for the Newtonian case and the non-Newtonian case were about the same. And I wanted to finally focus on this final behavior at the end where the outer colloid is suddenly stopped. So here's a movie that focuses on that final stage when the outer colloid suddenly stops and we see the relaxation of the center colloid. What is immediately obvious to you, hopefully, is that the colloid backspins and reverses in the opposite direction. It was spinning in the counterclockwise direction, but as soon as you stop it, the center particle reverses and backspins in the clockwise direction. This is kind of interesting. And if we perform this experiment across different realization, we all see this decay and backspin as a function of time. For the control experiment performed in water, we see that the data just has Brownian motion around exactly spot on the time that you stop the outer colloid. So clearly, viscoelasticity is creating some kind of interesting effect that's causing this reversal in the angular trajectory. And the first time I saw this, it reminded me of this toy. I don't know if people today play with them, but I remember playing a lot with them. It's a really fun toy. You store up the elastic energy by winding, and you just let it go, and the elastic energy just dissipates. Of course, for this solution, it's a viscoelastic fluid, so there's a viscous response in addition to the purely elastic response, but there might be some physics here that is applicable to the elasticity that we see here as well. Finally, one really cool observation that we found is that this decay of the backspin happens over the course of several seconds. That is an order of magnitude larger than the single relaxation time we measured from macro rheology using a conventional rheometer. So it means that there's something happening beyond the linear regime. For the linear conventional rheology, we're only weakly perturbing those worms. But with this experiment, we are winding many times, and so the fluid is exhibiting a nonlinear response. And so maybe the nonlinearity is somehow playing a major role in the regime where we stop it at the late stage. So I got kind of curious in what a linear Maxwell model would even produce in this case. So I went to my trusty old friend, ChatGPT, and asked the following prompt. Create a Stokesian dynamic simulator in HTML where I have one sphere held in the center and another outer sphere that translates in a circular motion around the center sphere. There's a far-field hydrodynamic force that will cause the center sphere to rotate. Both particles are torque-free. The surrounding fluid is a non-Newtonian linear Maxwell fluid. I want to vary the distance between the two spheres and also the translational velocity of the outer sphere. Color code the spheres with a half coding so that we can easily visualize the sphere rotations. I literally put in this precise wording and prompt into GPT-5, and this is what it produced. Here we go. So this is literally the HTML simulator that it just produced in a single line. I had to make one technical modification that Sachin was nice enough to tell me about, but it produced most of the features that are correct. Now, this simulator is pretty cool because, for example, I can change the size of the colloid. Let's change it to a bigger size there. I can also change, let's make it counterclockwise, so it's moving in the same direction as our actual experiments. And I can also change the relaxation time. Let's make it a little bit longer so that the effects are more dramatic. Okay, so now you can see the outer colloid spinning around, going around and around and around. The center particle is also responding to that hydrodynamically because I've told it that it has a linear Maxwell fluid constitutive equation. Now I can suddenly stop, I can click this button, stop motion, and then the outer colloid stops. So this experiment that I just performed is the same as what I just explained earlier with De Young's experiments. What you see is that the center particle slowly winds down and then stops at the very end. So let me just play that again. You can see the transient buildup. It's taking a long time for it to build up. So that part seems correct. And if I stop it, it just slows down. And what's interesting is that the outer particle also rotates, right? It also rotates, as it should, because that's also torque-free. And it's rotating because it's responding to a hydrodynamic interaction of a reflection from the center particle. So you can see it rotates less, which also makes sense. It should rotate less than the center particle because the center particle is receiving a direct hydrodynamic interaction. This particle receives a reflection back that causes it to rotate. So all the physics seems correct here, except for the fact that we don't see backspin. It just rotates in the same direction and it just slowly goes down. So there's something fundamentally different and missing from a linear Maxwell fluid that our experiments are exhibiting. So what is that missing piece? One obvious thing to do might be add nonlinearities to the Maxwell equation. Maybe it's the nonlinearities in the constitutive equation that could produce a reversal. So what we did is to ask a co-advised PhD student, Stokesian, who is advised between Professor Eric Schakfe and myself, to solve for the Oldroyd B constitutive equation, which is shown down here. So the top equations, the Stokes equations, Cauchy's momentum balance with zero inertia on the left-hand side, zero Reynolds numbers. This bottom equation is the constitutive equation that includes nonlinearities. This upside-down triangle is an upper convective derivative. It contains the nonlinear coupling between the velocity gradients. So there's a number called the Weisenberg number that tells you how elasticity, nonlinear elasticity, can couple into the viscous flow response, and that's all contained inside of this term. So this is a natural extension of the Maxwell fluid model, but including nonlinear finite Weisenberg number effects. So this is called the Olaroid B model. And there's a very nice drawing that I really liked, drawn by a fantastic student in Eric Schachfey's lab. This is a honeybee called Olaroid. Olaroid B. I really like this. I presented this at a Society of Rheology conference and people loved it. I think rheology people love it. It may not make much sense to you, but it's a nice symbol for this constitutive equation right here. What Stokesian did was he took these equations, immersed two boundaries using what's called a body-fitted code to numerically evaluate this equation inside this space. And after doing that, what Stokesian found is that the recoil, even with the nonlinear terms, was very small, negligibly small. We used a Weisenberg number of around 3 to 4, so pretty large Weisenberg number. So the nonlinear effects are definitely present. It should be in the model, except it didn't exhibit a lot of recoil. And at this stage, some of you might be wondering, well, maybe you could use a different constitutive equation. Maybe you can use, for example, a roly-poly model, which is used to model viscoelastic entangled linear polymers that incorporates repetition theory, tube models. You can go down the line of trying to come up with a better constitutive equation that incorporates features that are more similar to a worm-like model, a worm-like micellar fluid. Well, you can definitely do that, but at this stage, going through this example calculation, we start to notice major deficiencies in standard constitutive equations. For example, most constitutive equations assume a uniform distribution of polymer chains inside the fluid. The stretch and the conformation could vary spatially, but the center of mass of each of these chains are uniformly distributed and homogeneous throughout the system. But if you have some kind of forcing that causes heterogeneity of the entanglement sites or the polymers themselves, then the assumption of the homogeneous polymer is not a good one. And you can't use the standard constitutive equations that everyone's using. You would need to couple the density field of the beads to the stress tensor and the conformation tensor to come up with a more appropriate non-homogeneous constitutive equation. Also, most constitutive equations assume that the chains are very, very tiny and short and small. So even if you have a crazy flow happening, locally, if those chains are experiencing a linear velocity gradient, then that's okay. That's the underlying assumption present in almost every constitutive equation. But if you have long chains, like the worm-like micelles I just showed you, it may actually experience two very different parts of a velocity profile that may cause a breakdown of the constitutive equation assumptions that are built into those models. Finally, for this particular experiment, what we see is that the colloidal separation distance is of the order of microns, but the chains themselves, the worms, are also of order of microns. So you can have about a single chain that might traverse the entire interstitial gap. So there's a breakdown of the basic notion of the continuum approximation. We just don't have enough chains present in the interstitial region for us to have a continuum stress tensor at those points. And the interstitial region is where all the action's happening. So you want that region to be the most accurate. So all of these breakdowns in deficiencies in the constitutive equation made us aware that there's a lot of work that we would need to do in developing models for viscoelastic flows. So if there's no field equation available, and by the way, there's been decades of work done on studying worm-like micelles, both theoretically, experimentally. They're industrially super important, and lots of people have developed various models. And they're all very good models that describe different aspects of worm-like micellar solutions. But at this stage, we became more fascinated by what are the common deficiencies in general types of constitutive equations? So the goal of what I'm about to show you now isn't so much to describe worm-like micellars in particular or in specifically, but a general feature that we're observing inside our particular experiment. So what we can do is Sachet developed a discrete simulation of Stokesian dynamics. This is a simulation tool that can be used to generate hydrodynamic interactions between immersed bodies. So we have here our two colloidal particles, just like the experiments. And on the exterior fluid, we have a 3-linked polymer, which are very, very, very long. Okay, so they're designed to be long polymer chains that are connected just by 3 links. And they will respond hydrodynamically to the flows generated by these big colloids and vice versa. So they are talking to each other hydrodynamically. And Sachet will cause the outer particle to go around the center particle a couple of times and stop. And we'd like to see the response. And you can already see that there's a slow relaxation happening far beyond the relaxation of a single chain. When we stop that outer particle, there is a very slow relaxation happening that is far larger than the relaxation of a single chain going up and down. So we thought this may be the answer to our backspin problem. And in fact, if you actually go into the simulation and calculate the backspin of the center particle, you get a much, much bigger magnitude compared to the linear Maxwell fluid. And as a further confirmation, if you take these long chains and make them into a short chain, you get a negligible amount of backspin. So it's really the fact that you have long-range entanglement sites that are acting as weak springs that are compressing, that is generating this long, slow relaxation backwards. Now, what I'm going to show you here is a coarse graining of these polymer chains, where I'm going to plot one thing. I'm going to plot a particular point inside this polymer fluid. Measure the hydrodynamic force on that polymer bead at that point. Take a moment of that with the moment arm of the position vector. So it's x cross product with the hydrodynamic force experienced by that polymer. So in effect, it is how strongly it has the ability to generate a torque on the center particle. So let's watch this. So the bright yellow regions are the regions where there are a large magnitude of this cross product, meaning that yellow regions are generating locally a very strong torque on the center particle. And that's what's generating these torques that could cause it to go forward, but also cause it to reverse in the opposite direction. Finally, this Oloid B model clearly is missing things. It's missing the inhomogeneity, it's missing local velocity gradients, it's missing the continuum approximation breakdown. So there is a term that encodes all the nonlinearities, the breakdown of the continuum, all here. And until we can develop a field equation that looks just like this and move away from discrete simulations and come to a field equation like this, we can't make much progress in a problem like this. It would be great if we can have a good expression for this unknown term that encodes all the nonlinearities that we're now missing in simple constitutive relations. And in fact, a lot of what our lab is doing is trying to find this value right here called the kernel. This kernel tells you non-localities in space and time. If we were to flick one point in your fluid, how does that flick affect a different point in your fluid in time and in space? That's called a kernel. And if we can find what this kernel is, we can make some good models from that. And it's a very tricky problem that we are currently considering. But it would be really nice if we can come up with a field equation, because with a field equation, we can start to develop more complicated simulations. For example, there is no such thing as a viscoelastic Stokesian dynamic simulation. There only exists one for an incompressible Newtonian fluid or a linear Maxwell fluid. But for a general nonlinear constitutive viscoelastic polymeric solution, you can't do Stokesian dynamics of big colloids submerged in them. But it would be an incredibly important simulation tool to have if it were possible to develop one. even if we can't do it in computation yet, we can do experiments on them now. So we believe that this kind of experimental framework could be useful in developing kernels, developing nonlinear terms that we can't quite find, and at least test them experimentally. Because this experiment has the many-body interaction in an arbitrary, complicated, nonlinear Maxwell or non-Maxwell, other types of constitutive equations that we would hopefully like to drive. General complex fluids. Okay. The last thing I wanted to show you is moving away from water, moving away from worm-like micelles, moving away to a mystery fluid that is contained inside the bulk fluid. We're going to do the same experiment. We're going to take this outer particle, do donuts around the center particle, and we found a very interesting thing. What we find is that the center particle goes in the opposite direction, seemingly all the time on average. So earlier, it reversed in the opposite direction when the outer particle stopped, and that was the elastic response. Here, we're deriving the outer particle, and as we derive the outer particle, the center particle is spinning in the opposite direction. This would be like a negative viscosity fluid. Well, this is hot off the press data, and we're still thinking about exactly what's going on. With that, I'd like to end and thank the authors of this work, especially Daeyoung Kim and Sachin Nagela, who were the two co-first authors of this project. The papers that I talked about are here and here. I'd like to also thank Saksham, who's a student in our lab, and also Professor Eric Shakfe for collaboration on everything I talked about today. With that, I will see you guys next time. Bye!